In the previous slide, we found that Q forms an octonormal basis. What's so interesting about octonormal basis or orthogonal basis? In this slide, we'll remember that in 6.2.5, in the last slides, we talk about Theorem 8, the orthogonal decomposition theorem, and Theorem 10 for not an orthogonal but an octonormal decomposition. Let's recap. If W is a subspace of Rn and we have U1 to UP an orthogonal basis. An orthogonal basis means U1 dot U2 is equals to 0, UI dot UJ equals to 0 when I is not equals to j. But the norm of UI is not equals to 1. They are just orthogonal, they are not octonormal. Now, if U1 to UP are orthogonal basis of W, that means we have a very nice set of vectors telling us what W is, the minimum set of vectors that spans the space of W. We can easily approximate Y in the space of W by this equation. We do not need to solve it with this least square solution inverses to find the parameters. Instead, we simply can just perform individual dot product to get the parameter associated with each u. So this, you can think of it as x1 times u, and this guy is xp times up. What is x1? x1 is the weight associated with u1, which is found by the required vector y dotting with u1 divided by u1 dot u1. What about xp? Is y, the vector, dotting with up dividing by up dot up. Now, look at the bottom parameters. Is u1 dot u1. If u1 dot u1 is equals to 1 when the vector u is normal, this equation, theorem 8, reduces to theorem 10, because simply if you look at this equation, the only difference is that the numerator remains while the denominator u1 dot u1 is equals to 1. So theorem 8 and theorem 10 are the same equation when the norm of u1 is equals to, or the norm of the u columns are equals to 1. So to recap, we like orthogonal basis because it allows us to find the weights associated with each of these column very quickly. Now, you come to here. So if u1 and up are now octonormal basis, which is the q, so you can think of this q as the u now, then all we are doing is we can find the weights associated very quickly. But when you look at this equation, and if you put u into this matrix as UUT times y, then actually these two equations are identical. Okay, because y dot u1 multiplied by the u1 vector is actually ut u. So what happened is that we take the columns of u and we put it as horizontal columns. So this guy is ut and this guy is y, and we would get the parameters here. We multiply by u again, and this u would be perform for this from these columns of U. The name UUT is the projection matrix into the column space of, or the space of W. UUT is a projection matrix, and remember we typically call the projection matrix as P, and you can check that P square is equals to P, the property of a projection matrix. Lastly, how do we find Q from U? In this linear algebra course, we'll only teach you one of them, one of the three methods available. The method we are going to teach is the Gram-Schmidt decomposition. In the Gram-Schmidt decomposition, we are given the process, or we are given the matrix A, and we denote it by V1, V2, Vn, where we have n columns of the matrix, and we'll spit out U1, U2 up to Un, and these columns of Q will span the same space as required. Once we have found Q from A, then we can find R to complete the QR decomposition. For references, you can see some of these, especially MATLAB and such. Now, as a caveat, the idea is this. There's two types of decomposition by MATLAB. One is called the economy decomposition, and one is called the full QR decomposition. There are two types of decomposition MATLAB can perform, and you should know both of them. Here, I'll briefly state. Here, Q can be rectangle and same size as A. In the full, Q is a square matrix of size, in the size of m by n, it will be a square matrix of m by m. So for example, if we have a of 3 by 2, in the economy we'll have a 3 by 2 Q, but in the full we'll have a 3 by 3 Q. So you must know that there are different variations of QR factorization depending on the parameters sent to MATLAB or to Python to get is the decomposition. Python as in the NumPy package in Python. Thank you.